In this video, I'd like to introduce the idea of completing the square. So before we jump into some example problems, let's just talk about the main idea here. So we've seen in a previous video that if you have some quadratic where you end up with some squared expression, and this is equal to, let's say, 4, then once you've solved for the squared expression, or in other words, this perfect square here, then you can square root each side. And so the square root of something squared, those are going to cancel out. And technically, this will be equal to the absolute value of x plus 2. But in practice, the square and the square root cancel, and you just have to remember to put plus or minus on the right side, the square root of 4. And this plus or minus just accounts for the fact that there are two solutions. And we'll be able to prove that those two solutions make sense. So we have x plus 2 equals plus or minus 2. And when subtracting 2 on the other side, you can get your two solutions. So minus 2 plus 2 would be 0. And minus 2 minus 2 would be negative 4. And if you plug both of these in to the original equation, you will see that 0 plus 2 squared does equal 4. And negative 4 plus 2, which is negative 2, squared does again equal 4. So if we have this quadratic equation where it's some type of perfect square equal to something, then this is fairly straightforward to solve. So our goal is, let's say we have some random quadratic equation, plus 5x, let's say minus 9 equals 0. We want to transform this to some perfect square so that we can take a square root of each side. And this trick will allow us to solve every possible quadratic equation. And frankly, without this trick, quadratics are incredibly difficult to deal with because you can't just solve one side for x, or you can't even solve for the square term. Like, let's say we solve for this, we subtract 5x and add 9 to the other side, so you get 9 minus 5x, and we could try and square root each side here, but this is a very difficult expression to deal with. Anytime you have sums or differences under square roots, they are notoriously very difficult to deal with. And you have x on this side, but you have x on the other side. So you didn't really solve your equation for x. So this method won't work. And factoring something like this might be possible in some scenarios. But in most scenarios, factoring is incredibly difficult to do. So that's not a method you want to rely on. So people have figured out that if you are able to transform this quadratic into some perfect square, then it's fairly straightforward to solve because you can just square root each side. So let me erase a little bit, and we'll go back to this simple example problem here. How would we transform this to some perfect square? And the first thing I'm going to do is I'm going to isolate the x terms. So I'm going to get rid of this minus 9. I'll just put it on the other side. Now you could also just leave a space for it on the left-hand side, but a lot of people will just move it to the other side if that's possible. So we have x squared plus 5x, and I am going to leave a space, and this equals 9. Now, essentially, we want to add some number. Let's just leave a blank there, so that we are able to transform this into x plus some other number. Let's just call it a squared. But the question is, what number do we add here so that we can transform this into a perfect square? Well, let's start with this expression, this x plus a squared, and let's just multiply it out and see if we can notice a pattern. So x plus a times x plus a, if we use distribution, we have x go into both of those terms, so that's x times x, which is x squared, plus x times a, which is ax, and then the a distributes to both of those terms. So you have a times x, and then plus a times a. So plus ax plus, actually let me just make some space here. We have plus a squared. And if you simplify this, you get x squared plus 2ax plus a squared. Now if we compare this side to our quadratic, notice that the coefficient on x is 2a. So in this case, the 5 is 2a. Or in other words, a would be 5 divided by 2. So that's what we found so far. And the number that we're going to have to add to each side, notice, is a squared. And so if you square 5 over 2, you essentially just square the numerator and the denominator, and you get 25 over 4. So if we add 25 over 4 to each side, and you do have to do it to both, then we'll transform this into something that we can actually turn into a perfect square. So let me make that a little bit more clear. So we have this x squared plus 5x plus 25 over 4. And I'll just leave the right side as 9 plus 25 over 4. So this left-hand side here, this is a perfect square. This is now x plus a, and we figured out a was 5 over 2, squared. And just as an exercise, I encourage you to pause your video and re-multiply this out. Prove to yourself that this does, when multiplied out, give you this quadratic expression, this trinomial here. And again, once we have completed the square, now we could add these together using a common denominator, but I'm going to stop right here because in theory, now that we've gotten this perfect square, we can just take a square root of each side. And this might be a little bit complicated over here, but it can be done. And therefore, we'll be able to find two distinct values for x. Or in some cases, you just find one distinct value. That's essentially a repeated solution. So in all of these problems, you want to keep essentially this formula in mind, the formula for a perfect square, since we'll want to compare this coefficient on x to our a value. So let's look at one more example before we jump into the problems. Let's say we have x squared plus 12x minus 4 is 0. And you could try factoring, but this is not going to factor very easily. So let's complete the square. And I'll write down the formula down here. We had x plus a squared equals x squared plus 2ax plus a squared. And keep in mind, if you're going to use a formula, you should know where this formula comes from. So you should be able to derive this for yourself by rewriting this twice and then multiplying it out with distribution or the FOIL method. So from here, we want to isolate the x terms because we want to add some number so that we can turn this into a perfect square. So I'm going to just add the 4 to the other side. Like I said, if you want to just make a space and keep the minus 4 over here, that's a valid method as well. So we have x squared plus 12x. I'll leave a space anyways because we have to add a number. And then we added 4 to both sides, so it cancels out over here and becomes positive 4 over here. Now, matching this up with our formula, we want to change this into x plus some number squared. But to do that, we have to add a number first. And that number in our formula is a squared. So we have to figure out what a is. And a is half the coefficient on x. Or essentially 12 is 2a. Let me write that off to the side here. So we found that 12 is really 2a, or that a is half of that coefficient. It's 6. So we know our a value. Now the number we have to add is a squared. So if we square 6, we get 36. So if we add 36 to each side, we can turn this into a perfect square. And once you figure out what a is, you can just plug that in here. We figured out a was 6, so this is x plus 6 squared. And again, I encourage you to pause the video, re-multiply this out, and prove to yourself that these are equivalent, this trinomial here and this perfect square here. So you can see on the right-hand side, we get 40. And now, to finish the problem, we would just square root each side and solve for x. But you'd be able to get those two values for x. So this method will work for every possible quadratic equation. And eventually, we'll use it to complete the square on a more general quadratic equation, and we'll come up with the quadratic formula. So the proof of the quadratic formula, where it comes from, is this method of completing the square. So now let's go and look at these example problems.